Hello friends, this lecture I'm going to be talking about conservation of energy. Total energy of the system is conserved, and the total energy is called mechanical energy. And if there is no friction or air friction, this is the case actually. So we say generally, if there is no friction or air friction, the total energy of the system is conserved. Energy initial, or I'll call total energy ET, or total energy initial will be equal to total energy final. Let's say we have a child sliding down to a slide. So he's sitting here. Slide has a height, and as he comes down here, he will have velocity. Assume that the slide is on the ground. We take the ground level as zero level. And we will say that if there is no friction in here, the initial total energy of the child is conserved and is equal to final total energy. Initial total energy will be potential energy initial plus kinetic energy initial. Excuse me. And final total energy will be potential energy final plus kinetic energy final. If you look at this question in the beginning, the child does not have velocity, so kinetic energy initial will be 0. Again, the kinetic energy was equal to 1/2 mv squared, and potential energy was equal to mgh. The child will have a potential energy though, and it will be equal to mgh. And down here, height is 0, potential energy is 0. We take this to the 0 level on the ground. So the child will have 0 potential energy, while he will have 1/2 mv squared kinetic energy. So by entering these in here, energy total initial is equal to energy total final. We can easily solve for what is not known. Let's say we know h. H is 5 meters, and we're going to solve for velocity down in here, and we're going to find it. We can easily find it. And the initial, we have kinetic energy initial plus potential energy initial, and it's equal to kinetic energy final plus potential energy final. Now we enter all the values we found in here. Kinetic energy initial was 0 joules because 0 velocity there, and plus potential energy initial was equal to mgh. This will be equal to final kinetic energy 1/2 mv squared plus final potential energy 0. M's can be cancelled in here, divided by m, and we can easily solve for v. V squared will be equal to 2 times gh. V is equal to square root of 2 gh. 2 times 9.8 times 5 meters. Let's find what this is. I just made up this question, so it will be square root of 2 times 9.8 times 5 meters. So 9.89 meters per second. About 9.9 meters per second. If you notice here, generally in energy, we won't be needing the mass. On each side, the mass will be cancelled if we're dealing with conservation of energy question. This is generally the case, not always. Again, if there's no friction along the slide, the energy is conserved. If there was friction, we would have to take away the frictional energy. I'll get to that later. So we have initially potential plus kinetic minus the friction. The energy lost to friction here will be equal to final energy there. It won't be too much hard and stretched to solve it. It will be okay. We'll get to that later. But for now, we assume there's no friction. Energy is conserved. Initial energy is equal to final energy, and we can easily solve for what is asked in your question. If you also noticed in here, I assume that the level, the down level of the slide is 0. And we know from real life that it is not the case. Generally, there is a little height in here before the child jumps down. Let me call this h prime. I ignore this h prime. And this perfectly works for potential energy, because if I add this h prime, I would be adding this much of potential energy to this side to initial. So the left-hand side, I would be adding plus mgh prime in here. Right? And at the final also, we will have some final potential energy. Instead of 0, we will have mgh prime. So we'll be adding on the right-hand side the same thing. So these two things would cancel each other, and this is always the case. So in the questions of energy conservation, we can always choose any level that is appropriate for zero potential energy to ease our work. But what we have to do, we have to stick with this level. So if I choose this level to be 0 for the initial part, it should be the same for the final part. I cannot choose different levels for different parts in a question. Let me talk on that a little bit more. So choice of potential energy, zero potential energy level is important in a question. It is totally arbitrary, like the choice of plus minus directions in previous topics. But again, we have to stick with our decision. Choose a point as a zero potential energy point, and calculate the potential energies always. All points depend on this level we have chosen. For example, if we have, let's say, a roller coaster and it has a path like this, we have points A, B, C, D, and E. If I'm interested in points A and E, for example, so they are giving me a velocity here, VA, there are heights given, and asking me velocity here at point E. If there's no friction energy is conserved, and total energy in all these points are equal to each other. So we can say energy total at A is equal to energy total at B. It's equal to energy total at C, equal to energy total at D, equal to energy total at E. And since it's all over equations, I can deal with any of them. If I'm dealing with A and E, I can ignore all the rest of the parts. So I can directly say energy total at A is equal to energy total at E. And if I'm doing that, I can pick a position and ignore all these points calculations. I can pick this position, for example, to be my zero potential, right? And ignore the rest, find out what these heights are. I'll call this height A, I call this height E. And calculate the potential energies using height A and height E only. Ignore the rest. If I'm not dealing with B, C, D, I don't have to go there. I don't have to do all these calculations and lose time there. They should be aligned, by the way, not a curve. So this is the idea. If I want, I can choose any position to be zero potential, but I have to stick with it. So I can say then potential energy at A plus kinetic energy at A is equal to potential energy at E plus kinetic energy at E, and so forth. And potential energy at A will be mg HA, kinetic energy 1 over 2 m VA squared, and this will be equal to potential energy at E mg HE plus 1 over 2 m V E squared. Then I enter the values I know and solve for the values that I don't know. Probably will be only asked for one value. We know each value is for, let's say, and we know the velocity at A, and they ask us velocity at E. And if you notice throughout this equation, I can divide each term by the mass, and mass will be canceling. So even if, most of the times, even if they are giving you the mass, we won't be needing it. Sometimes though we will be needing it, so be careful there. But don't get confused. If they give you the mass and you don't need it, that could happen in energy questions. So let's solve a question now. And there's a nice question in here. Before going into this question, I want to tell you one more thing. We learned before that work is equal to change in energy, and we said this change in energy could be change in potential energy or kinetic energy. We said work is equal to change in energy, and we call this work energy theorem. So it could be kinetic energy change, potential energies. If there is both energies, kinetic plus potential, we look at then the total energy. If we're doing total energy, then we say work done is change in total energy. Simply we say work done is equal to total energy initial, total energy final minus total energy initial, or change in total energy. Or mechanical energy could be in some books. So this is the general version of work energy theorem. Work is equal to change in energy. It could be only kinetic energy change, it could be only potential energy change, it could be change in both, and it is equal to work. Now I can go into my question. Let me put it down here so we'll have more time to look at this equation. So we have a roller coaster in this question. Let me draw it for you. That has a path like this. We have the car in here. Car has 0 initial velocity. So it will move down, come down here, and come out there. And here it will have a velocity final as v. It is the initial level, and this distance height is given as h1 is equal to 25 meters, and this height is given as h2 is equal to 20 meters. And of course, as you can guess, what is the final velocity question is asking. So find the velocity of roller coaster in figure at finishing point. Assume the total mass of the roller coaster is 200 kilograms. Again, the total mass is given, but we won't be needed here. So what is the final velocity if the system is frictionless? This is also important. The question should say that, but it didn't. So frictionless system. Otherwise, the car would be losing some energy to frictions. So we will say the total energy is conserved if the system is frictionless. Energy total initial here will be equal to energy total final there. Energy total initial, potential energy initial plus kinetic energy initial, and energy total final is potential energy final plus kinetic energy final. Now in this question I don't have to deal with this part. And I'm going to choose this as my 0 potential level. Potential energy level. And I'm going to deal with this level as I am solving for the potential energies. And then height here will be equal to this height, 20 meters. And 25 meters I don't even have to take into account. So this is 5 meters. I can ignore that part. And I can write down my equation now in here. Total energy initial is equal to total energy final. Potential energy initial plus kinetic energy initial is equal to potential energy final plus kinetic energy final. And let's write these down. Initial potential energy is mg, this h, which is equal to h2 as well. So I'm going to put mg h2. Plus kinetic energy initial is 0, but I'll put it in here, 1 over 2m, v0 squared, v0 is 0, so this will be 0, because v0 is 0. Potential energy final is 0, because there is no height in here, this is my 0 potential energy level, plus 1 over 2m, v squared will be my final energy, kinetic energy, so then I can find v from here. So we are left with mgh2 is equal to 1 over 2m v squared. I can divide by mass each side, so I don't even need mass in here. Again, remind you, this is not always the case. If we were to lose some energy to friction, then it would change. 2gh2 is equal to v squared, and v is equal to square root of 2gh2. Square root of 2 times 9.8 meters per second squared times 20 meters. And this should be about 19.79 meters per second. Please check that and make sure it's correct. Recalculate it, will be a practice for you again. And you will be correcting me if I had a mistake there. We will be solving some more questions related to this in the lecture. Now I want to go into frictional case. If there is friction, what will happen, right? So let's move into there. Put a title, friction. Okay. Friction and conservation of energy. What happens? You might have learned, heard here and there that energy is never lost. In the universe, total energy is always the same. So if we are seeming to be losing some energy, it's actually converting into one type of energy to another type of energy. One system might be losing an energy maybe, but it's converting to another type of energy and passing to another system maybe. And we can see this in friction. Let's say we have a block that we are pulling with a force, right? We did questions involving these, and we assume there is no friction to a distance d. And the work done by this force, which is equal to energy change, right? We'll pull in this block, we're given it an acceleration. We know from Newton's laws that if there's a force, there's an acceleration. If there's an acceleration, the object mass will be gaining a velocity. And this velocity gives the object a kinetic energy. Now we learned, because kinetic energy is caused by velocity, 1 over 2 squared. So the work done for this force we said is equal to F times d. This is in joule, and we also learned work energy theorem that this is equal to change in energy. In this case, only kinetic energy. If there is no friction, this is the case. But if there was friction, there will be a frictional force, what we call and learned before Fk, right? And this is equal to mg mu k in this case, the frictional coefficient times mg, which is equal to n in here. I'm not going to go into those details, but what will be the frictional force doing here is a negative force. So this force is doing a work. I'll call this now work 1 by this force F. And the frictional force will be doing a work F, frictional force, frictional work, and it will be against the work done in here. It will be a negative work, and it will be equal to frictional force times the distance. And the total work done here will be work done by F minus work done by the frictional force. This will still be equal to change in energy. So it will be F times d minus F friction times d. And this is still equal to change in energy. And this is what friction does. It does a negative work. In terms of energy, it converts some of the kinetic energy here into heat. It converts into heat. We know that if we rub our hands against each other, they become hotter because of that. Due to friction in between two hands, some of the kinetic energy I have due to the force I'm applying and velocity I'm given to my hands converts into heat due to friction. So what happens is the energy is lost from my hands, but it becomes actually into heat. This becomes a kind of internal energy actually of my hands. We'll get to that later if we have time in the course. But that's what friction does. So if we are dealing with, for example, let's go back to the slide example. So a child is sliding, and he's gonna jump over here with a velocity. This velocity will not be the same if there was friction here. Let's say we had h, and at this part, only there was friction x distance, let's say. The child is starting, sliding, velocity 0. What we would do is energy total initial minus this work done by the friction right in here. So some energy will be converted into heat, will be equal to energy total final. And using this, we can still solve the equation. Let's say this is a distance, I don't know, 0.5 meters. And frictional force applied to kid is 10 Newton here. What is the velocity of the kid down there? And this is 5 meters. Let me see if that makes sense. MGH, okay, yeah, good. So this is 10 Newton, 0.5. Let's make this into a question actually. And 0.5 meters part of the slide has a frictional force is equal to 10 Newton. What is the velocity of the child as he reaches to the ground level? Now we will do total energy initial minus frictional work is equal to total energy final. Initially we have only MGH, I'm skipping the other parts, only potential energy initial, no kinetic energy. We put them in here, MGH. And kinetic energy initial is 0. Let's put them, so this is new, we'll learn better. 0 joule kinetic energy minus the work done by the frictional force will be frictional force times the distance. So 10 Newton times 0.5 meters will be 5 joules of work taken away from this initial. So this will be work done 1 over 2m v squared. Here we would need the mass of the child. If the force is given, the frictional force is given, some part is taken away. We cannot cancel m anymore. So let's say the mass of the child is also 10 kilogram. Put them in here. 10 kilogram times 9.8 meters per second squared times the height 5 meters minus this 5 joules is equal to 1 over 2 10 kilograms times v squared. And we solve for v squared from here. Let me carry that to here and solve it. Actually, I don't have an answer for it. I just made it up in here on the spot. So I'm taking this up in here. I have 10.9.85 times 5. Let's do that. This will be 98 times 5. 490 joules. 490 joules minus 5 joules there is equal to 5 v squared. So 485 divided by 5 in square root will be equal to v. So velocity is about 9.8 meters per second in here. 85 meters per second. So what we did is there was an initial energy, some part of it is taken by the friction, it's equal to final energy, and solve for the velocity. And in this case, we had to include the mass. Finally, I'm going to tell you about some other types of forces and power, and we'll be done with this lecture. Some other types of energies, and power, and we'll be done with this lecture. We won't be going into too much complicated questions with all these types of energies included. We might be solving some medium hard questions. So you should be able to follow up and understand nicely. So let's see, additional type of energies. We have spring potential energy. What is also called elastic energy. We know from general life if we pull a string and leave it will be oscillating because we give it some energy and leave it. This is the spring potential energy we give it. And the harder, the more we pull it, the larger the energy will be, and the oscillation will be larger as well. So if we have a spring, let's say along horizontal, and we put the distance x, the spring pulls the distance back with a force, and this force does a work, and this work is equal to spring potential energy actually. The force is called spring force, and is equal to minus k times x. F is equal to minus kx. Minus is due to the reason that whichever direction we're pulling it, the force will be against the direction of this pull. So if we push the spring, we know that the spring will push him back. If we pull it, and spring will pull him back in opposite direction always. This is called spring force. This is also called Hooke's law actually. And the energy will be called spring potential energy, or called ES or PES would be better maybe. Potential energy, let me call it PS, is equal to 1/2 kx squared. As in the normal force case, if we have a force versus distance graph for a spring, for example, x meters, the area under the curve will still be spring potential energy. So area will be equal to spring potential energy. Sometimes it's also called U spring in your book, or E spring. S means for spring potential energy. It's also called elastic energy, because if you have an elastic and pull it, it works like the spring. And K here is the spring constant. So if we have a spring, the value of spring constant should be given to us. It's intrinsic to the type of the spring, and it's constant. This is one type of energy. Another type of energy is so we can put here one spring potential energy, and leave it here 1/2 kx squared, and the other is gravitational potential energy. We talked about gravitational potential energy as mgh. This is correct for masses on Earth, and for small masses, if we are close enough to Earth, the g seem to be constant, but it's actually not constant if we go really, really far away. So for large masses, let's say large celestial bodies, then we have to use another equation. Let's say in between Earth and the Moon, or International Space Station, if there is distance r in between their centers, the gravitational potential energy we will call Eg will be equal to minus g, gravitational constant, or universal gravitational constant, m, Moon, and Earth divided by r. If you remember, gravitational force was the same, equal to r squared. This is only the gravitational force multiplied by the distance. The negative is due to the fact that if we move the objects too far away to an infinite distance, the energy becomes zero. So moving closer gives us negative energy. So the far away infinite distance is 0 point, closer to the Earth is negative, and the other side, which we can never go, is positive. But that's how we deal with gravitational potential energy. Only question we could ask here is maybe what is the value, and we put negativity in here and calculate it, and that's like gravitational force. Something nice could come out of this though. If we assume the gravitational potential energy in between an object on Earth, let's say me, and I want to jump out of Earth, I want to jump very fast with a velocity, which I will call V escape. Very hard that I want to get out of the gravity of the Earth. In order to be able to do that, my kinetic energy, 1/2 mv escape squared for my escape velocity, should be equal to magnitude of the gravitational potential energy in between me and the Earth. And this will be now our Earth, because the distance in between me and Earth's center is our Earth. So instead of r, I put our Earth. And my mass cancels in here, and the escape velocity for me can be calculated as v escape is equal to square root of 2g m Earth over our Earth. This is the escape velocity for Earth. For any celestial body can be calculated. It's not dependent on the mass of the object. It depends on the mass of the planet and the radius of the planets. The universal gravitational constant is a constant. So we can do some problems involving escape velocities, and that's all. So gravitational potential energy for large masses is not the generally we deal with gravitational potential energy as mgh for small masses on Earth. This is how it is calculated. Let me see here. Any other? Okay, let's touch into that as well. Additionally, as a third type of energy, we learned about rotational motion and angular velocity. Since angular velocity is also a type of velocity, we can have a rotational kinetic energy. So there's another type of energy, rotational kinetic energy. And if there is a rotating object that has omega rotational angular velocity, its rotational kinetic energy, I'll call this k rot. It's equal to ke rot would be also good. 1/2I omega squared. And the first question to ask here is, what is I? I is moment of inertia. And its intrinsic value depending on the object's total mass and the type of shape of the object. There are equations to calculate that. For a sphere, a solid sphere, for example, so if you have a sphere solid full inside, it has a mass m and radius r. You don't have to know that. The moment of inertia for this will be 2/5 m r squared. There's a whole list of how to calculate moment of inertia if you need to. Generally, it will be given in the question. And we can solve the question right now. Actually, there will be a question generally asking what is the kinetic rotation kinetic energy of an object with an angular velocity, let's say 2 rad per second, which has a moment of inertia as 2 kilogram times meter squared would be the unit for moment of inertia. Kilogram here times meter squared. And the unit for energies, all type of energies, of course, as you can guess, is joule, always. I have a whole list of equations for calculating moment of inertia in my notes, and I'll post them online soon. Let's solve a question here. Yes, okay. I think that's all three types. Spring potential energy or elastic energy, gravitational potential energy for large masses, and rotational kinetic energy are the types of energy I was talking here. Of course, there's heat, internal energy, and so on, but we want to cover them in here. Let me solve my example for rotational kinetic energy. An object has a moment of inertia of 1 kilogram meter squared. So an object has a moment of inertia of 1 kilogram meter squared, and it rotates at a constant angular speed of 2 rad per second. So angular speed is 2 rad per second. What is the rotational kinetic energy of the object? So KE rotational is asked. That is equal to, of course, KE rotational is equal to 1 over 2I omega squared. 1 over 2, 1 kilogram meter squared is I times omega squared 2 rad per second squared per second squared. It will be 2 joules. As simple as that. It could be rotating tires of a bicycle or a car. They all have rotational kinetic energy. Now if we have, let's solve this as another example. If we have, let's say, a wheel of a bicycle that is rotating with an omega and also moving with a velocity, then this will have two types of kinetic energy. Rotational kinetic energy, as we learn now, and the usual kinetic energy we know, right? Let's call this translational, so going along. So total kinetic energy will be kinetic energy rotational plus kinetic energy translational, which will be 1 over 2 I, again as the moment of inertia, I omega squared plus 1 over 2 m v squared. So total kinetic energy will be two types, rotational plus the translational. If an object is rotating plus moving along a line, linear line, like in this wheel in here. Okay, and last thing I'm going to talk about is power. It's quite simple and quite short topic I'm going to talk actually. Power is described as the work done per unit time. So power, work done per unit time. So if we know a work W and the time as T, power P will be equal to work divided by this time. And before we know the work is equal to change in energy, so we can also find power of a system using change in energy divided by time, right? Just to remind you, change in energy is always equal to final energy minus initial energy being the total energy of the system. Unit for power is what? So unit for work or energy is joule. So joule per second is equal to what? Joule per second. And with a large W, we show the unit watt. Okay, it's not too long. Let me solve this power question I have in here, and then I'll let you go. Okay, you and your friends are making an experiment. I'll just put this in this little corner over here. It's quite a short question, but it will fit. So there are steps. There's height of the steps, and you're running on top of the steps. And your friend here is keeping the time. The faster you run, the more powerful you would be, because if time is smaller and you're doing the same work, your power will be larger. So if you climb up in here, the work you do will be the change in energy. You had, well, the energy is changing. You had zero potential energy in here. You're climbing up, you have some kinetic energy, and it's all converted into potential energy in there. So the energy change will be generally this potential energy. Total potential energy will have up in here. So you can use that. If your friend finds the time, you can measure your power actually. And let me read you the question. While you're running on top of stairs, your friends records the time it takes to be 10 seconds. So the time is recorded to be 10 seconds. Calculate your running power. If your weight is 50 kilogram, here you will need your weight, 50 kilogram. And the height of the top of the stairs from the ground is 4 meters. So this is 4 meters. Your weight is 50 kilogram. My light is gone again. Alright, it's back. Sorry about that. What is your power? So we'll calculate work done by you, which is the change in energy. Energy final minus energy initial, right? Your energy initial is 0 joules. You have 0 velocity, 0 height, so 0 joules. No need to spend time there. Your energy final is equal to mgh. Let's calculate that. Your m is 50 kilogram. G is 9.8 meters per second, and h is 4 meters. So final energy you have is, I must have it somewhere in here. No, I don't. Let me calculate that. 50 times 9.8 times 4. 1,960 joules. This is your final energy. And change in energy, which is equal to work, is equal to E final minus E initial. E initial is 0, so 1960 joules is your change in energy. The time is 10 seconds, so you can just simply calculate your power as change in energy, or work divided by the time. 1960 joules divided by 10 seconds, so 196 watt is your power. So that is it. We're going to solve some questions tomorrow in class. Please try to understand what is done in here to be able to follow up tomorrow. And see you tomorrow.